So welcome to our Have Lunch with Artificial Intelligence course. Thank you for all coming. So you've seen the advertisements around on this in the campus, and we welcome you here with the group. I'd like to acknowledge our predecessor in this. Many of you have been to the Great Powers Competition course. How many of you have been there? A lot of people. So we're following in their footsteps. We thought that was a great idea, and since artificial intelligence is a big deal in the strategic thinking of the Navy and the Defense Department, we thought we'd follow on by just copying the success of the other one and do one for the artificial intelligence topic. So artificial intelligence is a major strategic concern. On this campus, we've started to formulate our own response to the DoD Navy concerns around this by forming an artificial intelligence consortium, which now has over 60 faculty members involved in it from all over the campus. And this is our first major public activity here, this course. The purpose of this course is to present you with an overview of the artificial intelligence field, to demystify a technology that has been encumbered by lots of hype, to give you a language for discussing and thinking about artificial intelligence, and leave you with a conceptual framework which I think will help orient you in your future discussions. And of course, we're going to try and be non-technical here and emphasize the basic concepts and principles. And if you're really interested in all the technical details, we have courses that you're welcome to come and take. I myself, I'm Peter Denning. I'm a computer scientist. I was minted as a computer scientist in the 1960s, back when this field was pretty much still in its formation stages. I'm right here at NPS. I've been at NPS for almost 18 years now. I'm currently a distinguished professor and chair of computer science department. I've been teaching computer science for, believe it or not, over 50 years. That's a long time. I've seen many things come and go in the computing field over the years. So I think I've developed certain perspectives just from that. I have to confess that artificial intelligence was not my first interest in computer scientists, even though down the hall from my office as a graduate student was the Artificial Intelligence Laboratory at MIT. I was more interested in operating systems and networks and just trying to get the basic technology working. At that time, nobody knew how to do a lot of the technology that we have. The technology of the internet and the operating systems has gone on to be a major infrastructure for artificial intelligence today. A lot of what we do in artificial intelligence today would not be possible were it not for the high-speed networks and the operating systems that we use to talk to them. I'd like to tell you a little anecdote about my first direct contact with artificial intelligence. It was at the time I was wandering around the country doing my faculty interviews. One of my stops was Stanford University at the Artificial Intelligence Lab. They had an appointment over there, and they wanted to show their favorite experiment at work, which was a robot arm that stacked blocks. So they had a table with 3 white blocks on a black tablecloth, a TV camera, and a robot arm connected to a computer. And the idea was I, as the guinea pig, could come and put the blocks anywhere on the table. The robot arm would then pick them up and put them into a neat stack on the side. So they showed me this and let me rearrange the blocks any way I wanted, and I was really impressed. This was really an impressive demonstration. And they said this is one day going to evolve into robots and become the future of artificial intelligence. So I was very turned on by this. I said, how does this work? I was all excited about this. And so they told me how it worked. And it turns out it used an obscure theorem from geometry to detect 3 identical white cubes against a black background. And using the theorem, they could tell you the exact positions of those 3 cubes in space and then obviously move the arm to stack it. But it was not possible to do it for 2 cubes. It was not possible to do it for 4 cubes. They all had to be the same size. They all had to be white. The tablecloth had to be black. Because if any change in any of that, the whole thing would fall apart. And there was no way to generalize it. They had no idea how they would do 4 blocks. They had no idea how they could do different size blocks. So I figured that this sounded pretty flaky to me, and I wanted to go work on operating systems, which I understood better. Well, I can tell you that after all this time, I've come on board. I'm now on board with artificial intelligence. There's been a lot of technological process. There's a lot of stuff there that is scientifically grounded and generalizable and is very useful. And that's what we want to talk about here in this course over the next 20 lectures. So what's going to happen here is at the beginning of each lecture, I'm going to give a short introduction to the topic of the day and introduce you to the speaker, who's typically one of our computer science faculty, knowing something about artificial intelligence, but there's faculty from other departments around the university helping us also. And then after that lecture, which will be about 30 minutes, we'll have a question and answer session. So that's our plan. We're also video recording these lectures because we want to put them up on the NPS YouTube channel for other people who couldn't be here today or other days to have a chance to see at least what we were talking about. There's a lot of interest in this topic. So that's our general plan. So I'm going to be giving you the introduction to this topic that we're talking about today, and also on Wednesday, our 2 lectures are introductory. Then after that, we're going to have the other faculty coming and talking to you about specific topics. Let's talk about what we're here for. We're here in this next period of time, this quarter, to explore artificial intelligence. So we want to answer the question, what is it? I assume a lot of you have that question, what is it? So we're here to help you answer that question. We also want to explore what are its benefits and risks, and what are its military significance. So we're going to have a lot of discussion around all those topics. We're also interested in establishing a common language that we can use to talk about artificial intelligence. So we have a way of grounding our conversations and having intelligent conversations. And with a precise language, we're in a position to cut through the hype and find out what's real about artificial intelligence. On the bottom here, I've written down one of our mottos to keep in the back of our mind is don't confuse utility with intelligence. We have lots of very useful programs and machines that have been built in the name of artificial intelligence, but they actually aren't intelligent. That's going to be one of our messages, but they're extremely useful. The artificial intelligence field got started formally in 1956, although there were people interested in this topic before 1956, but it officially got started with a conference of the leaders of artificial intelligence at that time. And over the years, it's been buoyed by enthusiasm and also plagued by lots of hype and overpromising. So the researchers promised more than they could actually deliver. This little graph on the bottom here shows a phenomenon that's kind of unique to the artificial intelligence field and not to all of computer science. This field has had severe ups and downs, booms and busts. So the graph shows you periods of going up and then a couple of crashes that have been labeled by AI researchers as AI winter. So we had 2 AI winters, and they were both caused by overpromising, and the funding agencies of AI research got disillusioned and said, you guys aren't delivering. We'll come back when you've got something you can actually deliver. So that's why we had those two things. But now we're in a third period of increasing success and increasing interest. So that's part of the history of the field, and it has influenced the field. Here's the same picture. I've annotated it with some of the technologies of artificial intelligence that were developed during those three boom periods. And you can see they were very productive periods. There's long lists of technologies. If you just take a look at some of these things, you'll see some of the familiar things you've probably heard about artificial intelligence. For example, way back in the 60s, we were doing speech recognition, early versions of board games like chess and checkers, language translation, or shall we say the attempt at doing language translation, simple robots like that robot arm at Stanford, modern problem-solving systems, the kind of things where you could take word problems that your kids might do in school and just say the word problems to the computer and it would work out the word problems. My daughter would have loved that if we had that machine. The neural networks were first described at that time. They've become very popular in the recent time, but they were first described then. And a variation of neural networks called perceptrons, which were early attempts to do vision, were described at that time. The second boom, we came up with more advanced things, expert systems, a knowledge revolution, technology called deep neural networks, which we'll be talking more about during this course. Techniques of statistical inference to figure out things that look like human beings, figuring out intelligent things. Automatic classification of large data sets. New memory models, sparse distributed memory, a thing going on in the computational sciences community called the grand challenges. These are advanced computational tasks in all parts of science. Artificial intelligence played a role in those. And an important thing in Japan, started around 1980, was the fifth generation project, where Japan said we are committed to building artificial intelligence supercomputers. And that spurred the US government to get back into the funding game and started the next boom, which lasted for a while, but then it also fizzled out as, once again, we made too many promises that we couldn't keep. And finally, when it started to resurrect again, some of the stuff you hear about recently, like data analytics, deep learning, image recognition, conversations such as Siri and Alexa on your computers, grandmaster chess players and Go players are new developments, human-machine symbiosis, driverless vehicles, automatic fire control and weapon systems, swarms, drone swarms, and cyber defense and offense. All these are new topics that artificial intelligence has gotten involved with in the last few years and has made some significant contributions to. Well, when we go back to this thing, what is this phenomenon that's been going on all this time? What is artificial intelligence? Here's some images that show some of the concepts. So the first one in the upper left is Lee Sedol, the Korean Go master playing AlphaGo, the machine that beat him. Down below is a Hollywood conception of Battlestar Galactica. Some of you have watched that TV show. It's a great TV show. Up at the upper right is a scene from the Terminator, which is one of our big fears, that somehow the artificial intelligence machines will decide they don't like us and try and terminate us. And down at the bottom right is I'm not sure exactly what the photograph is, but it's supposed to depict a swarm of drones looking for something interesting to do. So these are some of the sort of popularized images that we have of artificial intelligence, but it doesn't really tell us what it is. Well, the popular notions include things like thinking machines, conversation machines, puzzle solvers, game players, speech recognizers, vision recognizers, and expert systems. And there are probably a few more, but these are some of the terms you've heard. Also, there's a lot of Hollywood out there. So there's These are the titles of movies that you've probably seen. I've seen them all. Some of them are pretty nifty movies, but they paint pictures of the future that don't make a lot of sense. So there's the Terminator movies, Skynet, iRobot, Battlestar Galactica, Ender's Game, Commander Data, a character in one of the Star Trek series, and R2-D2, the famous robot from the Star Wars. So there's a lot of Hollywood conceptions about what artificial intelligence can do and what kind of dangers it presents. And again, it's easy to get confused and ask what's real and what's not here. What can we actually do? What can't we do? So let's keep pushing on this. What is artificial intelligence? Well, again, you got these conceptions, and now there's things that worry us based on news reports that we hear. For example, automatic weapon systems that take over and start firing and maybe start a war or a conflict that no human being wants to start, but the weapon system manages to start it. Drone swarms becoming so numerous in the number of drones in the swarm, they become a new weapon of mass destruction. Some of you might have seen a video on YouTube the last couple of years called Slaughter Bots, which is a scenario about drone swarms becoming weapons of mass destruction. Then there's mastering large battle spaces. Is this possible? If the other country or entity could master the space better than us, can they beat us? Another thing that's really troublesome to a lot of people is that when an artificial intelligence machine or software reaches a conclusion and makes a recommendation, and you say, why did you recommend that? It can't give you an answer about why it did that. So you wind up in a state of confusion. Should you trust it or not? Because it can't explain itself. Another area of concern is mass surveillance and control, and also massive unemployment, a possibility that people could get pushed out of jobs by these machines. Well, let's see if we can dig a little further. So seriously, what is artificial intelligence? Well, the very first thing that we could say about it is it's computers doing intelligent things. Computers doing tasks generally considered human intelligent tasks. Well, that's very nice, but wait a minute. What's intelligence? If we're going to have computers do it, we ought to have a better idea of what it is that computers are doing. Well, what is intelligence? Well, one of the problems we face with intelligence is it's ill-defined, that nobody has a standard definition of intelligence that everybody would agree to. And whatever definitions they do have aren't scientifically implementable as a machine. So there's a kind of story or joke that goes around the AI field, call it the moving goalpost story, which says when a machine does it, we look at the machine and we say, that's not intelligent, because the machine is doing it. So in other words, we set a goal for ourselves, like playing chess. If we can get a machine to play chess, it would have to be intelligent. So 30 years later, we have a machine that plays chess, beats the world grandmaster, and we look inside the machine and we say, there's no intelligence there. So where did the intelligence go? So this is one of the problems that plagues us. When we try and define intelligent, the goalposts keep moving and nobody will agree on exactly what intelligence means. So one of the things we should be careful about in all of these things is intelligence is not speed. If something goes fast, it doesn't mean it's intelligent. A race car goes fast, doesn't mean it's intelligent. An airplane goes fast, doesn't mean it's intelligent. Well, if a computer goes fast, it doesn't mean it's intelligent. Machines can now do 1 billion calculations per second or more. Your human brain can do about 1 calculation a second. So you're intelligent, but the machine is not. Your laptop and your nearest supercomputer are very fast, but they're not intelligent. So what is intelligence? Well, one of the earliest attempts to try and answer that question was by Alan Turing, a famous pioneer of the computing field. and he invented something that came to be known as the Turing Test. And first thing he did in his article about that is he said, nobody knows what intelligence is, so we're not even going to try and define it. We're going to come up with an alternative here, which he called an imitation game. If I could design a computer and a human being through a curtain could converse with me or the computer, how long does it take the human being to figure out which one is the computer and which one is me? And if it takes a very long time, then we'll say the computer has successfully imitated the human being and has successfully simulated intelligence. If it only takes a couple of minutes, then we say it's not intelligent. So Turing's idea was there's a computer and a human. There's some kind of an interface like a curtain or a computer screen or something, and I'm an interrogator who can ask questions and try and have a conversation with both of these entities, but I don't know which one is which. And my job is to see if I could distinguish the two. So one of the basic questions is, how long does it take the interrogator to distinguish the computer from the human? If it takes a long time, then we say the computer is successfully simulating intelligence. If it takes a short time, you say it's failed. Well, the other side of it that says, even in the case where the computer is seen to be indistinguishable from a human, is it intelligent? A lot of people will say, well, simulated intelligence is not the real thing. Simulated digestion, which we could do, you could simulate the chemical processes of digestion, is not nutritious. If I'm a physicist and I simulate a black hole on my computer, I don't get sucked into it, nor does my computer. The simulation is not the same thing as the real thing being simulated. So the same thing is true in intelligence. If I successfully simulate intelligence, so everybody in the room says that's intelligent, is it really intelligent? We don't have an answer for that. So somewhere along the way, the word artificial got added to this to try and distinguish the real kind of intelligence from what a machine can do. So intelligent behavior by a machine gets called artificial. So it's simulated intelligent behavior. If a machine says, I am intelligent, do you believe it? But wait, we're still not done. What's a machine? So we went from asking the question, what's artificial intelligence, to intelligence, and then we saw we can't directly answer the intelligence thing, so Turing came up with a test that tries to help us distinguish a computer from a machine. What's a machine? It's like chasing turtles all the way down, trying to find the base turtle here. So what's a machine? Well, a machine is an apparatus of components that automates a process humans want done. Machine grants an advantage, such as amplified force or speed, that humans do not naturally have. So there's an obvious interest in using the machine. The human is partially or fully out of the loop, so the machine can do some or all of the work. A computer is a machine that has hardware and software components, and it implements a function, an input-output function, defined by an algorithm. So if I give you an input, you apply the algorithm to it, it generates an output. That's what a computer does. So that's a machine. We know how to build electronic circuits that do this. One of the problems that we have with machine is a problem that I call anthropomorphizing, which means that we're projecting our beliefs about intelligence or our hopes of intelligence onto the machine. So these are some common things we say here when we do this, like the computer is an electronic brain. Or something more simple, like the computer knew where I was. We're ascribing the ability to know to a computer. Or the computer thought the input was wrong, so we're ascribing the ability to think to a computer. The computer understood my problem, so we're ascribing the ability to understand to a computer. Well, these are all anthropomorphizing. Nobody's yet built a computer that knows anything, that thinks anything, or understands anything. When you look at what we've built so far, you look at it and say it's only a machine. It has no brain. It doesn't know, think, or understand. So what can it do? Well, the machines can do a lot of things. If you make a list, on the left side here you see capabilities that humans have. On the right side you see capabilities that machines have. They're not the same list. They complement each other. Humans sometimes wish they could do calculations better and logic better, search for things better, retrieve data better than they actually can. But on the other hand, humans can form social communities. They have empathy, compassion. They make commitments and judgments. They invent things, and they're sensitive to the context in which they do their work. Machines, on the other hand, do the calculations, logic, search, retrieval, comparisons. They never get bored. And they're also context-free. Let me say a word about context for a moment. So, some people call this the context problem. So the machine is operating in a context. Humans operate in a context. Can the machine sense the context? Can a human sense the context? Well, obviously, we think we can. We spend a lot of our time trying to understand the context in which we're working, but can a machine do that? So when we talk about context, we're talking about the human ability to sense issues unstated in the background of our experience and then bring them forth to give meaning to what is around us. So that's what we mean by context. There's this subtle, elusive phenomenon of pulling stuff out of the background to give meaning to what's in front of us. Can a machine do that? Well, machines don't sense context. In fact, machines are designed purposely to not sense context. They're made out of parts that deal only with local signals. So a particular electronic circuit gets signals from its neighbors and produces outputs that go to its immediate neighbors. The electronic circuit does not consult any larger context in order to figure out what it should do when it receives signals. It doesn't consult any larger context to try and understand what the signals might mean. It's simply a circuit that says, when this signal comes, do that. So that's a very powerful thing to do. So we've removed the encumbrance of reading the context. Machines, therefore, can go extremely fast. So machines, the way we build machines now, anyway, maybe some future machine will read some context, but no existing machine reads context. So there's no known way to formalize this idea of bringing forth from the context. And as long as there's no formalization of it, you can't get a machine to do it. So I point this out because the speed of the machine comes from the design that purposely does not look at context. So we get something we want, which is speed, and the cost is no context. If we wanted to have it read context, it would probably slow it down to our speed, which wouldn't give us a speed advantage. So the challenge that we face today in trying to talk about all this is that, first of all, we live in a world where AI machines do exist. There's lots of them. I showed you some at the beginning. And they do very useful things. None of them is intelligent. If you go look at any of the AI machines that have been offered up and look inside and say, what's going on here? You won't say that it's intelligent. You'll just say it's just a machine. So none of the machines that exist today are intelligent. So what we want to do is take that reality and explore and assess the powers of these machines without, in spite of the fact that we don't have a clear definition of intelligence. We don't want to anthropomorphize, so we want to talk about what the machines can do and not what we hope they can do. And we also do it without expecting machines to sense context. So the approach we'll be using in this course, we're going to begin by classifying AI machines, the artificial intelligence machines that do exist, by their learning power. So the reason we chose learning power is that we always associate intelligence with learning, so there's some correlation there. It also turns out that we can define what learning of a machine does. You say, machine learns something when it acquires a new capability that it didn't have before. So it's operating and its function changes as it operates. And we say it learned something, it learned a new function. Well, we can rate machines. We can say if I have two machines, A and B, and A can do things that B can't, then we'll say A is more powerful than B. And we can do that with learning power. So we can say, let's see what we could do by organizing machines by learning power, which ones are more powerful, which ones are less, and do that. That's something we scientifically can do. We don't have to have a definition of intelligence to do that. So that's what we'll be doing in this course. Is we'll start out especially with a classification of artificial intelligence machines and what their learning power is, so you can see lots of examples. And then we'll talk about some of the specific domains of application where these machines have been used and what's been accomplished there. And then we'll talk about future implications, strategic implications, and other related things like that. Well, the machines hierarchy, we'll introduce that in the next lecture on Wednesday, and we'll have a series of guest lectures after that going into the individual machines in the hierarchy. So there's six lectures on this general topic. Let me just give you a little quick overview. Here's the 6 levels, 0 through 5, basic automation, rule-based systems, supervised learning, unsupervised learning, human-machine teaming, and then aspirational machines. So the basic automation refers to the type of automation that we grew up with, like autopilots, factory assembly lines, these kind of things that automate things. They don't actually learn anything while they're doing anything. So we have that here simply to give us a baseline. So the traditional unintelligent automation is the starting point. We won't even call that artificial intelligence. We'll just say that's where we're starting from. Level 1 was the first generation. In that first boom, there's a lot of systems that tried to do rule-based, which basically says we'll tell you the rules of intelligence, whatever we think they are, and the machine will follow the rules. We'll tell you the rules of how to translate one language to another, and the machine will follow the rules. We'll tell you the rules of how an expert accomplishes problem solving, and the machine will follow the rules. So that's what that category of system was at the top. Those machines were program machines. They did not have any capacity to actually acquire new learning. You had to, if you wanted to have them expand their function, a programmer had to come and do something to the machine. The second level is supervised learning, which means that we have machines that we present them with inputs and outputs. We say, this is the function we want you to learn. Here's an input, here's an output. And we just keep on presenting load, example after example after example, and after a while the machine learns how to translate inputs to outputs according to what we want. But it's supervised because we're standing there saying that's correct or that's not correct. The third level is unsupervised. So we're going to take away the external agent that tells the machine when it's doing the right thing. The machines that learn how to play chess and Go do this. They have two machines playing against each other, and when a machine wins a game, it gets a reward for winning, which it then translates back into reinforcing the moves that led to that outcome of winning. So over a period of time, machines can play against each other and gradually kind of teach each other how to play the game and become a winner at it. We'll talk about that. Human-machine teaming refers to combinations between humans and machines. This is where most of the productive work in artificial intelligence is actually happening right now. Is teaming up, using a machine to provide functions that humans aren't good at, and using humans to provide things that machines aren't good at. Together, they're better than either one could be. And finally, the last one there is aspirational machines, which are the ones we dream about, and we've been dreaming about for more than 50 years. So we'll talk about what are some of those and what are the likelihood they'll actually get built. Here's the same list with the names of the professors who will be in to talk to you about this. So you'll meet these professors in the coming lectures. So that's basically the overview of artificial intelligence I want to give to you. It gives you a little bit of a sense of what we're trying to explore in this course, and who's going to be talking to you about some of the things that we will be discussing. We also have some websites for the course. You can take note of these. The first one there is a web page for the AI consortium I mentioned at the beginning. So it gives you an overview of what this consortium is trying to do, and it contains links to this course. The second URL there is the direct link to the schedule of the course. So if you ever get lost, you say, where are we in the schedule? What classroom do we meet in? Take a look at that second URL. Also, after the lectures are finished, when we get the production of the video recording, we'll put a link on there to the video recording. We will include the slides that were used in today's lecture as a link on that schedule. And we'll also ask the individual lecturers if they have one item that they recommend for you to read, to give you a link to that. So that'll be available on the web page, and it'll be incrementally added to as we go along. So keep those web pages in mind. Well, anyway, so that is my summary of what we're trying to do here, and my introduction to the AI field and the story we're trying to tell you as the course unfolds.